in this worked example, we'll revisit the example from the lecture. There we looked at what happened at the forces on a block on a slanted surface. Here we're going to take it one step further and ask, under what angle can I slant a table or tilt a table such that a book that lies on it just does not slide off? So what we want to know is, how far can you tilt the table before the book starts to slide? First step with a problem like this is to make a sketch of the situation. So we have a table. I don't really care much about the table, so I'm going to draw it as a straight line with maybe some little small lines to show that this is a table. And I have a book that's lying on it, and since I have nice colors here, I'm going to use one and draw the book like that. All right, so that's my sketch. Second step is to put in the forces that are acting in this system. We're interested in what happens to the book, so I'm going to draw the forces on the book. Now, which forces are there? Of course, there's gravity, which is always pointing down. There's going to be a normal force from the table on the book, because the book is not falling through the table. And there's going to be a friction force, and since the book tends to slide downwards, the friction force between the book and the table is going to be pointing upwards. And we know there's a friction force because there is a normal force between the book and the table, and because the book and the table want to move with respect to each other. So there is now a friction force acting upwards. And we're going to tilt the table, so I should define the angle that the table makes with the horizontal. And I'm going to give this angle a name. I'll call it theta. All right, so now the question is, for which value of theta will the book just start to slide down? So when it just starts to slide down, it means that, well, that's the same angle as the point at which the forces are just still in equilibrium. We've seen in the lecture that the friction force is a bit of a weird force, right? Remember, the friction force would go up to a certain maximum value, right? Go up to a certain maximum value, right? And then go down a little bit and then be static, right? So the friction force in this linear regime, it would be less than or equal to a coefficient times the normal force. So, which makes sense, right? If you're not pushing the book at all, then there's not going to be a friction force, which is, for instance, is the case if the table is horizontal. However, if we start tilting the table, the book will want to slide and the friction force will increase. What will also happen is that the normal force will actually decrease. And the reason for that is that the component of the gravitational force that's perpendicular to the table will start to decrease. To see that, what we have to do is decompose some of these forces so that we can look at perpendicular components. But what we see here is that the friction force is parallel to the table, the normal force is perpendicular to the table, and the gravitational force has a component both perpendicular and parallel to the table. Of course, we could decompose all forces in x and y components, but it's easier to take a component along the table and perpendicular because two of our forces already are uniquely in those directions. So in that case, we only have to decompose the gravitational force, which gives us a component that's perpendicular to the table and a component that's along the table. Now, how big are these components? Well, you've probably seen this before. The angle theta that the table makes with the horizontal, since the gravitational force is vertical, right? The angle theta also occurs here. And then we know from basic trigonometry that this component is the magnitude of this component is the magnitude of the gravitational force times the cosine of theta, and this component along the table goes with the sine of theta. If you don't see the angle, there's also a simple trick, right? Imagine in your head that we turn the table back to horizontal. In that case, the component of the gravitational force along the table disappears, and the sine of theta is 0, whereas the component perpendicular to the table is equal to just the gravitational force itself, and indeed the cosine of 0 is 1. All right, so now we have two forces that are perpendicular to the table, namely the normal force, which is always perpendicular, and the component Fz cos theta. And if the book is not moving in that direction, these forces better be equal. So we have that Fz times the cosine of theta equals the normal force. We also have two forces along the horizontal direction. One pointing downwards, one pointing upwards, and if the book is not moving, these two also better be equal to each other. And so we have that the Fc times the sine of theta equals the friction force. So this is perpendicular to table and parallel to the table, but under the condition that the book or the block or whatever, if the book is not moving. So at which point will the book start moving? Well, that of course is when the frictional force has reached its maximum, which by the theory we've just discussed is when the frictional force equals the coefficient, the mu k or mu s, right, depending on whether you're still in the static regime or in the kinetic regime, times the normal force. So if the book is just about to start moving, right? So this is not always true, but when it is about, but this is then mu f n. Right? If and of course, if I made a little mistake, I see this of course is the static one, right in here. So since we're turning the table slightly until the point that the book is starting to move, this should be the coefficient of static friction. All right, so now we can start combining these two equations and say, well, we have here an equation between the gravitational force and the normal force in the second line, but also in the first line, so I can use the perpendicular to the table rule, this one, the first one, to find the normal force and substitute it back into the second one. So if I do that, I get that gravitational force times the sine of theta equals us times the normal force, which is Fz times the cosine of theta. And we see that it doesn't actually matter what the magnitude of the gravitational force is here, because it will just drop out. So the mass of the book doesn't matter, and actually not even the gravitational acceleration matters. So if we would do this experiment on the moon, we would get the same answer. All right, so we can slash those things out. And what we find is that the angle is that angle for which the coefficient of static friction is the sine of the angle divided by the cosine of the angle, which of course is the tangent of the angle. Usually I would leave this as my answer. Of course you could invert this and say that the angle theta max is the arc tangent of this coefficient of static friction. Now, of course, you could look up the coefficient of static friction of a given book of a given material and a table of a given material and actually put in numbers and find what this actual angle is. Inversely, you can, of course, now determine what the coefficient is by measuring the angle at which the book will start to slide. So what did we do in this example? Well, before we conclude, it makes sense to check our answers. First thing to check is, do we have the same kind of number on the left-hand side and the right-hand side of our equation? Right? We can't compare forces with masses because we can't compare apples with oranges. All right, so on the left-hand side we have an angle, which is expressed in number of radians or degrees, but has no unit. On the right-hand side, we have the arctan of a coefficient, which also has no unit. So indeed, we have number equals a number. No meters, seconds, newtons, or anything. The second thing is, well, if this coefficient would be higher, we would expect the angle to also be higher because the maximal frictional force that there could be before the book starts the slide should be higher. And that indeed is the case. And if the coefficient goes to 0, then making just a very small angle will already cause the book to slide, which indeed is also the case. So indeed, our answer makes rudimentary sense. So, what did we do? First, we made a drawing. We put in all our knowledge, in this case, all our vectors of our forces. Then we decomposed them in components perpendicular and parallel to the table, and from that we wrote down these two equations, equations 1 and 2 over here. And then we combined those equations to get to our answer, and we check that our answer actually answers the question, right? We were asked for the angle, and that our answer makes sense.